In this presentation, we'll look at some considerations that go into physical level design. Previously, we'd seen this graphic representing three-level architecture in a database system. We have the physical level at the base. This is where the data is actually stored on disk. We have the DBMS, which is the conceptual level, which is how we see the data, for example, tables, rows, and columns. And above that, we have the external level, which is how programmers, end users, and administrators, among other groups, see the data. With this presentation, we're going to focus on the physical level. Some physical schema terms that you may hear about in the context of this presentation include physical media, which are the disks, we think of them, where the data is actually stored. Now, when we store data on physical media, we're actually storing them in physical records. These are sometimes also called blocks or pages. This is different than logical records. When we think of table rows, what we're actually talking about are logical records. Remember, the conceptual level is how we see the data. Table rows are logical records. They're not necessarily how the data is stored on disk. When we talk about a file, what we're really talking about is a collection of physical records organized for efficient access. It's up to the DBMS to take those physical records and show them to us as logical records. Files provide persistent storage, and that's something that's very important in database terms. So when we talk about a physical record, it's important to remember that multiple logical records can exist in one physical record. And that's one distinction you can draw. You have a physical record on disk, and it may store many logical records. And again, logical records are how we see the data in terms of rows. When it comes to maintaining data, the DBMS provides the organizational structure, but the operating system provides the access and storage functions, whether that be Windows, Linux, the Macintosh. The goal of any good DBMS is to limit the number of physical record accesses. This is important because it slows things down to be hitting the disk. Many of you no doubt have dealt with a computer where the hard drive light has been on almost consistently because it's working very hard. It's just not fast enough for the things you're asking it to do. As a result, things get very slow. When we talk about limiting the number of physical record accesses, one thing that we're often talking about is the difference between nanoseconds and milliseconds. There's a great level of difference between these two concepts. Nanoseconds are how we often associate memory access, like main memory, and milliseconds are often how we talk about accessing hard drives. Now, as we move into more flash-style solid-state hard drives, this gap will shrink. However, for large data sets, the gap is still very important. Most database management systems use buffers, what you might call in-memory caches, to improve the efficiency of updates and retrievals. Again, using the power of main memory and its relative speed advantage versus secondary memory. As a result, disk access is the limiting factor in database performance. Why? Simply because it's much slower than using main memory. Here's a conceptual view of how the DBMS uses buffers. Buffers are normally used for data that's currently being looked at, examined, modified, or that may be more frequently looked at, examined, modified. So the DBMS in its software uses these buffers to help speed access to frequently used data or data that's being used at that point in time. The idea being it's much faster to retrieve the data from main memory than from the physical disk. So the goal of physical database design is to create a design providing the best response time at the lowest cost. In other words, how can you create a database, a table space, an organization so that you can get at the data in the quickest way with the lowest cost? Now, cost here doesn't mean necessarily money. Often money factors in, of course. But when we talk about cost here, we're talking about CPU speed, CPU usage, memory usage, and disk I/O required to access the data. Obviously, we want to minimize that as much as possible. Our response time is the time required to access the data we request, for example with a select statement, or to update, insert, or delete. So how can we create an optimal situation? Let's talk about a few key things. A rule of thumb that we often want to keep in mind is that retrieval performance is often inversely related to update performance. This is important because you want to know how the database is going to be used, at least how it's going to be used most of the time, so that you can tailor your design to that need. Physical database designers often strive for some sort of balance in their design because many databases are both frequently being updated and frequently being queried. So what factors might impact the design decisions that we make? We need to know how much data will be stored now and in the long term. Now here we're not talking about exact amounts, but we want some idea of scale. How fast is the database expected to grow? For example, over the next month, over the next year. The reason this is important is the amount of data will impact the distribution of that data, how we spread the data across perhaps multiple systems, multiple disks, you name it. We have to think about how much data we have, because that will impact how we're going to organize where the data actually goes. Remember that the performance for large tables can be increased by storing the logical records in more than one file or on more than one disk. Remember, the logical records are the rows, the way we see the data. Under the hood, so to speak, at the physical level, we can actually structure our tables to store all the data within one table across multiple disks, across multiple files, across multiple systems. We also want to know how the data is going to be accessed. It's often helpful to know the frequent queries, reports, and applications that will be run. How is this database going to be used? Is it going to be primarily a web database for an e-commerce store? Is it going to be something that will simply provide information at the end of every month to the sales team? What are the common reports that will be run? What are the common queries? And what are the applications? Each of these things will help to get an idea of how the database will be used, and we can tailor the design to make it more efficient for those purposes. We also might want to know if queries are either fixed or ad hoc. If queries are fixed, it means we know them in advance. They may be common reports that need run or queries that generate reports. Ad hoc queries are more the what-if type of analysis. And again, we can use this information to help tailor our design to be a bit more efficient for one or the other. These are just some of the considerations that go into physical database design. Physical database design is not a huge part of this course, but I wanted to give you a brief example of the kinds of things you would think about. With Chapter 8, they talk about things like distributed databases in a bit more detail, and I encourage you to read that. But keep in mind that it's always good to know what the client wants to do with the technology before you actually go and build it.